This conference will now be recorded.
Hello everyone. So we will start with the problem, but after that there will be discussion related to rest of the compounds of boron and aluminium. So there are basically 3 compounds of boron, and out of which only one discussion is left, which is Diborane B2H6, and under aluminium we will also have 2 more compounds. So we will discuss boron and aluminium compounds in today's class. Now this problem is related to H3BO3, that is boric acid. Now boric acid, its preparation, structure, properties we have already seen in the last class. So based on this we have to solve this problem. So here we have total 4 statements, and we have to find that which of the following statement about this compound is not correct. So out of 4 statements, 1 statement is not correct. We have to find that. The first statement is saying that it is strong triabasic acid. Now the formula is H3BO3, and at a first glance it may seem that there are total 3 hydrogens, so it must be triabasic, but actually that may not be so. Now H3BO3, what type of acid is it? That is whether it is Bronsted acid or Lewis acid. Those discussions we have already done in detail in the last class. So based on that we can say that triabasic acid means all the 3 hydrogens can be replaced, but it is actually not so, which will be clear once we see how it is behaving as acid. Is it Lewis acid or Bronsted acid? Now the next statement is saying related to preparation. It is prepared by acidifying an aqueous solution of borax. Now this is actually true because Na2B4O7, that is borax, when it is treated with mineral acids such as hydrochloric acid or H2SO4, whatever it is, in both cases there is formation of H3BO3. So this statement is true that if we want to prepare it starting from borax and there will be some acid, then there is formation of H3BO3. So second statement is fine. The third statement is related to its structure. It is saying that it has a layer structure in which planar BO3 units, that is several BO3 units, join to each other by hydrogen bond. Now here the equation that you are seeing, that is related to its acidity property. I will come to that later, but before that look at its structure. So this structure we have already seen. And here you can see several BO3 units, how they are connected to each other. The pink dotted line, that is actually the hydrogen bond. So hydrogen bonds are present, and that is why in 2-dimensional region, several H3BO3 molecules, they are forming some links with each other, and as a result there is formation of a layer, and then different layers are stacked with each other. That is different. But how the BO3 units are joined, that is obviously by hydrogen bond. So this is also true. Come to the last statement. Last statement is also related to its acidity property. So first statement and last statement, these two are related to its acidic property. Now look at this equation. When H3BO3, this is H3BO3, when it reacts with water, what is happening here? Here, water molecule, if you consider its structure like this, then the OH unit of water, that is actually coming towards BOH3. So it is accepting HO minus, and as a result, now we are getting BOH4 minus, which is basically this structure. So one more OH is now connected to boron, and there will be overall negative charge. And the H part, that is removed in the form of H plus. So basically what is happening here, the statement if you read, it is saying it doesn't act as a proton donor. So here H3BO3 in presence of water, it is not donating any proton. None of these OH bonds are broken. So it is not donating any proton, but it is accepting HO minus unit from water. That means it is accepting some electron negative charge from other species, and that is the definition of Lewis acid. When it accepts some negative charge on lone pair, that means it is Lewis acid. So it is not Bronsted acid, because the definition of Bronsted acid is if it is donating some proton. Just take example of HCl, it donates H plus and Cl minus. And in presence of water, this H plus together with water molecule, it forms hydronium ion. But here the case is not like this. Here it is accepting HO minus unit. So that is why it is Lewis acid, but it is not proton donor. And remember, as ultimately overall we are getting 1 H plus. It is true that it is coming from water, but ultimately we are getting 1 H plus. So you can say that it is as if monobasic acid, but we cannot say that it is tribasic acid, because 3 times we are not getting H plus from BOH whole 3. Overall there is only 1 H plus, and that is also coming from water. So it is not tribasic, it is basically monobasic, and its behavior is Lewis acidic types, not Bronsted acidic types. So that is why here which of the following is not correct, this will be the correct answer, the first one. Fine. Now we'll start the last compound of boron, which is diborane. So total 3 compounds were there. In last class we have finished borax Na2B4O7, and after that there is boric acid or orthoboric acid, which is H2BO3, regarding which we have just discussed one problem in the previous slide. Now the third one is diborane, and the formula you can see B2H6. There are actually several binary compounds of boron with hydrogen are there, and they are called as boron hydride or borates. So binary compound means any compound which is formed from 2 specific elements. So here boron is one element, another element is hydrogen. These 2 specific elements are involved in boron hydrides, and there are different types of boron hydrides or borane. And you can find the similarity if you consider its pronunciation. It is just like alkane. So in alkane, what we know, it is hydrocarbon, there is carbon and hydrogen present. So just like that, it is also we are calling these binary compounds of boron and hydrogen as borane, just like alkane. Only difference is now we do not have carbon, only we have boron. Now, among these different types of boron hydrides, the simplest one is diborane. Now, it is actually the dimeric form of BH3. BH3 is the actual compound, because we know if you consider valency of group 13, it is basically 3. And according to that, it should be BH3, but it remains in the dimeric form to remove its electron deficiency. And that part we will discuss in the structure topic, not here. That is what is the actual reason for which it forms dimer. That we will discuss separately. But remember, BH3 it remains as B2H6 dimer form. It doesn't remain as the monomeric form, which is BH3. So the simplest boron hydride, that is boron hydrogen related compound, is diborane, which is B2H6, the dimer of BH3. So as we always start with the preparation methods. So we will see here first industrial method. That means industrial scale means when you are preparing it in large scale, then what reaction method is used. So diborane is produced on industrial scale or large scale by the reaction of boron trifluoride. So here as the source of boron, we are using the compound boron trifluoride, and as a source of hydrogen we are using sodium hydride, which is basically containing H minus. This is, if you write in ionic form, it is Na plus H minus. And we are getting B2H6, 6 NaH, 1 BF3, sorry, it will be 2 BF3, and we are getting B2H6 along with sodium fluoride. Laboratory method, that means if you want to prepare it in small scale, then what you will do? It can be obtained in small quantities. Now the reaction is, we have now taken the source of boron, the compound is sodium borohydride, NaBH4, and there is also iodine. So in presence of diglyme as solution, so diglyme is basically not solution, I mean solvent. This is actually ether type of solvent. If you want to know its structure, it is MEO, then CH2 CH2O, then again CH2 CH2OMe, symmetrical type of structure. So remember, diethyl ether we use as solvent, which is ethyl group, then oxygen, then again ET. So this is also just like another ether compound, and it is symmetrical compound. So diglyme is used as solvent. In presence of this type of solvent, and sodium borohydride reacting with iodine, we are getting B2H6, and there is also formation of sodium iodide and hydrogen gas. So this is the small scale method. Now another method we will see. Again we are using BF3, and BF3, though in this reaction we have written it as BF3, but as it is electron deficient compound, any boron compound with 3 bonds, it is actually electron deficient, because surrounding boron, if you consider only 3 bonds, surrounding boron there are actually total 6 electrons. So it is always electron deficient. And just to compensate that deficiency, with BF3, it remains as etherate complex. So etherate is Et2O. Et2O is ether, O Et group, Et group. Now BF3, as it is electron deficient, this lone pair of oxygen, it will behave as Lewis base and it will be given towards BF2, and as a result they will form some adapt type of compound, and we write the formula as BF3 dot Et2O. It is basically Et2O, it is donating electron through oxygen atom towards boron atom of BF3. Now this is the starting material, that is the source of boron, because we are trying to prepare B2H6. And we have now taken lithium aluminium hydride, okay, which is reducing agent. Now boron trifluoride etherate, when it reacts with lithium aluminium hydride, we are using the solvent diethyl ether, which is just like diglycine. Remember in the previous equation we have seen. Now we are using diethyl ether as solvent, and we can prepare diborane. B2H6, here the other compounds produced, lithium fluoride, aluminium fluoride, and this Et2O part is removed. Okay. So these are the different methods for preparation of B2H6. Now we will see the structure. So it is diborane. As in BH3, boron atom has only 6 electrons surrounding it. So that is why 2 BH3 molecule. Now they are forming the dimer. In monomer, there are total 6 electrons surrounding boron, as you can see here. So that is the reason why it remains in the form of dimer. And as here, if you look at this arrow is longer, this arrow is shorter. So that means mostly it remains in the B2H6 form. Now the structure that you are seeing, these two bonds, you can also consider it as if it is, this is one BH3 part, this is another BH3 part. But these two bonds, it is written in as the normal bond, but the other bonds, that is this BHB bond, it is drawn as dotted. So these two bonds are not same type of bonds, there is some difference. So the bonds that you are seeing in these two terminal position, I am writing here T. So these hydrogens are terminal hydrogens. So that is why I am writing T. And the middle hydrogen, that is the bridging hydrogen, because it is forming as if forming a bridge between two BH2 unit. Okay. Now this BH2 and BH2, both side, they remain in one plane, and the two hydrogen in the middle position, they remain in the perpendicular plane. So don't think that here all the atoms, that is BH3, both the units, they are in the same plane. No, that is not the case. The BH2 units, they are in one plane, and if you imagine a perpendicular plane, in that plane, this part is present. Okay. Now, if you consider when I have said that these two bonds, terminal BH bonds and the middle BHB bonds, these two are not similar type. Now, what I'm trying to mean here, these red electrons that are basically coming from boron. I am again drawing it with red, and the blue one, that are the electrons of hydrogen. Right? Now these terminal bonds, as you can see here, these are normal 2C2E bond. 2C2E bond means 2 center 2 electron. So any normal covalent bond, it is always 2 center 2 electron. There is 2 center, left hand side, right hand side, and in between these two you have 2 electrons. that is a pair of electron in a particular covalent bond. So this is fine. But what is the bond that you are seeing in this pink region, that is actually different. Now here, to remove the electron deficiency, we have said that it forms dimer. But what it actually means? It actually means if you consider this part as if this is one BH3 unit and this is another BH3 unit, right? Now, these two electrons, they are basically over, it is spreading over this region. So as if there are total 3 center BHB, 3 center, but total number of electrons in this 3 center is 2 electron. So that's it why this pink color region, this bond is called 3C2E bond. And because of similarity in structure with a banana, it is also called banana bond. Fine. Now, how the electron deficiency is removed? If you just focus on any particular boron, just focus on this right hand side boron. Now, surrounding this boron, here we have 2 electron this side, then another 2 electron. Now, consider this pink region. Here we have 2 more electrons because these 2 electrons, they are actually spreading over this whole region. So it is also part of this boron. So here we have 2 more electron and here we have 2 more electron. That means surrounding this right hand side boron or the left hand side boron, now there are total 8 electrons. So though it is not normal, that is all the bonds are normal, not normal 2C2E bond, there is both 2C2E bond and 3C2E bond, but still electron deficiency is somehow removed. If you simply compare with the monomer unit and if you compare this structure, obviously electron deficiency is to some extent removed, and that is the reason why it forms 3C2E bond. Okay, that is the banana bond. So there are 2 types of hydrogen, remember. One hydrogen is terminal hydrogen, so these hydrogens are terminal and these 2 are bridging. So here the 4 terminal hydrogen atoms and the 2 boron atoms, they lie in one particular plane, and the remaining 2 hydrogen, suppose remaining 2 hydrogen, marking it with B, one lie above and another one is below the plane. So they are actually bridged hydrogen. Now if you look at this structure, the third structure, so this is one plane where the BH2 units are present, and another plane is this plane, that is perpendicular, where these 2 hydrogens are present. And one more thing, if you notice here, this bond is 131 picometer, but the normal 2C2E bond, it is 118 picometer. Okay, and from the angle you can understand how, that is what is the orientation of these atoms. But 3C2E bond, this bond is longer and this bond is shorter, okay, which is clear from this value. So this is the structure, unique nature of its structure. After structure, next we have to see properties. So how, what is this physical state? It is colorless pyrophoric gas. Look at the boiling point, 180 Kelvin, very, very low. And at room temperature, it is pyrophoric gas. So if boiling point is 180 Kelvin, obviously room temperature, it will be gas. There is a sweet odor, it is colorless gas, it is toxic also. Action of heat. So if we heat this compound, what will happen? It is stable only at low temperature. But if it is heated in a seal tube, look at the temperature in this temperature range, then a complex series of reactions can occur. Why I am saying complex series? Because so many different types of compounds along with liberation of hydrogen gas is possible. If you see, we have not used any equation here. It is simply written as if B2H6 you are heating and there is formation of different types of boron hydride. It may be B4H10, B5H11, B6H12. So the ratio of boron and hydrogen atoms, these are also varying. So that is why it is mentioned here as complex reaction occurs, complex series of reaction occurs, producing different types of higher borons. Why I am saying higher borons? Because it is 2,6. But now see, number of boron is high. And also there is liberation of hydrogen. But among this commixture, if you particularly, suppose you want to produce this one selectively, then you have to control the reaction condition in terms of temperature, pressure, or the duration of the reaction, all these things. So by controlling it, we can prepare any particular compound. Okay. How it reacts with oxygen? So as it is pyrophoric, so obviously there will be vigorous reaction with oxygen, and it is exothermic. Now look at the value of del H. It is negative 2035 kilojoule per mole. So from the value itself, it is clear. Its vigorous nature, how much vigorous it is. And what are the products we are getting? We are getting B2O3. It is oxide of boron along with 3 water molecule. So it is very highly exothermic reaction. Reaction with water. When it reacts with water, there is formation of boric acid and also hydrogen gas is liberated. Next reaction is reaction with ionic hydride. Now ionic hydride means in hydrogen chapter we have seen there are different types of hydrides, and when I am saying ionic hydride, mostly the metals from S block, they form this type of hydride. So there will be cation, there will be anion. So these are examples of ionic hydride, lithium, sodium from S block. So lithium hydride, it is basically Li plus H minus, sodium hydride Na plus H minus. When diborane is treated with these metal hydrides, that is ionic metal hydrides, there is formation of metal borohydrides, and there is presence of tetrahedral BH4 minus unit. Why it is tetrahedral BH4? Because the 4 hydrogens surrounding boron, they are in tetrahedral environment. So that is why it is tetrahedral unit, and as that is in general you can write it like this, LiBH4, but if you consider its positive negative charge, it is lithium plus, and overall in BH4 unit there is overall -1 negative charge. So that is why it is written in this. Okay, sodium borohydride normally we write as NaBH4, but if you consider its charge, it will be Na plus BH4, total -1 negative charge. These products are used as reducing agent in organic synthesis. In organic compounds, lithium borohydride, sodium borohydride, these reagents are used frequently as reducing agent because they can be the source of H minus ion, hydride ion. And they can also be, another application is, they can also be the starting material if you want to make some other type of borohydride. So these are lithium and sodium borohydride. But suppose we want to make some other type borohydride, we can use these compounds as source. So these are the applications of this type of compounds. Reaction with methanol. So trimethyl borate is formed. BOCH3 whole 3. So as if surrounding boron, there will be total 3 OMe group. B2H6, 1 B2H6 reacting with 6 CH2OH and forming 2 trimethyl borate, and there is also H2 gas production. Next reaction we are going to see is reaction with halogen acids. Now halogen acid means HX type of acid, that is HF, HBr, HCl like this. X is halogen. So diborane reacts with halogen acids and they give halodiborane. That means if you consider the formula B2H6 of diborane, if you replace one hydrogen with X, now it will be B2H6H5X. So one hydrogen is removed. So one hydrogen is removed here and another hydrogen is also in HX. So these two hydrogens together will produce H2 gas. If you look at these equations, B2H6 reacting with HI, B2H5I is produced, H2 gas is liberated in each cases. So same type of compounds we are getting. But though equations are similar type, but if you consider reactivity, obviously this one is most reactive, after that HBr and then HCl. So this is a reactivity order. And as HI is reactivity is maximum, and which is clear from this reaction condition. See, when you are doing the first reaction, that is you are treating B2H6 with HI, you can do the reaction at 323 Kelvin even without any catalyst. But if you want to do the same with HBr or HCl, now you have to use in presence of their aluminium halide. Their aluminium halide means if you are treating B2H6 with HBr, you have to use the catalyst AlBr3, which is Lewis acid. It will act as Lewis acid. If you are treating it with HCl, then the acid you have to use AlCl3. Okay. So that is it is written. That is the respective aluminium halide you have to use as catalyst. So it is clear from this reaction condition that you have to provide catalyst, means now the reactivity is becoming, it is less compared to HI. So that is why we need to use some catalyst. Okay. Next reaction is how it is reacting with ammonia. Now this is very interesting because when it reacts with ammonia, the compound that is formed, borazine or borazole, that compound has some unique structural aspects, and based on that problems are, you can get problems. Okay, so it is important to know the details of the structure of this molecule. Diborane compounds with combines with ammonia and it forms first this type of adduct. So it is as if Lewis acid, Lewis base type of adduct. So ammonia is the Lewis base here. Now B2H6 to ammonia, though we have written it in this way, but actually it should be formulated like this. See, BH2 2NH3, there is a positive charge. So BH2 as if it is plus, and another unit is BH4, which is minus. If you count the total boron and hydrogen, it is actually B2H6, but you have written it in this way. And with this positive part, there is two ammonia molecules associated. So that is why BH2 NH3 whole 2 overall charge is positive. Ammonia is neutral molecule, so it has no contribution towards its charge. It is still positive charge. Overall charge is positive, and BH4 minus. So first this will be produced. See, 3 B2H6 reacting with 6 ammonia. There is formation of this molecule. So these two are 1:1. That is, if you have taken 1 mole B2H6, you will get 1 mole of this ionic compound. But after that, when this will be produced. Now, if you are further heating it at 473 Kelvin, there will be some decomposition. Ultimately, it will give borazine or borazole, which is having formula B3N3H6, and hydrogen gas is liberated. It is totally balanced equation. If you count hydrogen, nitrogen, boron, you will see both sides is same. Now, though we have written the formula as B3N3H6, but if you actually see its structure, it is very interesting because the structure has some similarity with benzene ring. So this is the structure. It is actually cyclic compound. Okay. Here we have B and B bonds alternative, and with each boron, each nitrogen, there is one hydrogen atom attached. So that is why B3N3, but H is 6, total 6 hydrogens. Now here, as if you focus on boron atom, they are actually electron deficient because surrounding boron there is total 6 electrons, and we know nitrogen, it has lone pair. Now because of this lone pair, now this lone pair can be donated towards boron, and when it is donating boron, there will be some double bond formation. It is back bonding from nitrogen, it is going towards boron. So there will be some double bond formation between boron and nitrogen. Fine. So the direction of arrow as you are seeing here, but I can also draw the arrow in a different way. Suppose this nitrogen is now donating this one. Now this one is donating here. So the alternative direction is also possible. So the structure that we will get, it is like this. So nitrogen, as it has donated electron to boron, now there is positive charge over it and negative charge over boron. So two alternative structures are possible depending on which side it is donating. So suppose I am numbering it here, number 1 nitrogen, this is 2, this is 3. So in the first structure, this is first structure, this is second structure. In the first structure, number 1 nitrogen, it is donating electron towards this boron. But in the second structure, this number 1 nitrogen, it is donating electron to this boron. So two alternatives are there. So that is the two structures are mentioned. Now you can find the similarity. Sorry, there will be one more bond here. You can find similarity with benzene ring. So in benzene ring also there is alternate CC double bonds, right? Now, though we are saying it has similarity with benzene, but remember in benzene, all these bonds are basically carbon. But in this case, all the atoms are not same. You have two different types of atom. You have boron, you have nitrogen. So here the bonds are basically completely non-polar because both the atoms are same. There is no electronegativity difference. But in this case, the bonds between boron and nitrogen, obviously there is some polarity, which is also clear from the charges because nitrogen is donating. So though in benzene there is delocalization, here also pi bonds are there, delocalizations are there, but don't think that delocalization intensity is same in both. Obviously in benzene the delocalization is very high. It has similarity with benzene, but it is not completely same. So because of this similarity, we call this molecule as inorganic benzene. It is isoelectronic. So total number of atoms, if you consider in the whole molecule, it is same. Boron is having atomic number 5, right? Then nitrogen, it is 7, and in between these two there is carbon. So as if you consider benzene, there is only carbon, but in inorganic benzene, that is boragene, there is boron and nitrogen. So after all, you will see total number of electrons are same, and also it is isosteric. That is, if you consider any particular atom, so if you consider carbon in benzene, it is for forming bond with 2 more carbon and 1 hydrogen. So total 3 bonds, that is 3 coordination is there. Here also the same thing. If you consider nitrogen or boron, it is also there are total 3 direction it is forming bond. So that is it is isosteric, it is isoelectronic with benzene, and its structure is similar to that of benzene. This is the reason we call it this molecule inorganic benzene. But remember, accept the fact that in benzene the pi electrons are completely delocalized because it is non-polar. But in borazine, they are partially delocalized. Complete delocalization is not possible in case of borazine. Remember, here delocalization is not as pronounced as in the case of benzene because in benzene there is only non-polar bonds, but here the electronegativity of nitrogen is greater than boron. So there will be some polarity. Even if you consider this single bond, there will be some polarity. Electrons, because nitrogen is more electronegative than boron. Okay. Next reaction, that is chemical properties of diborane. How it reacts with alkalis. They dissolve in strong alkali like NaOH, KOH. It produces metaborates. So here we are getting, because we have taken NaOH. So in the product side, we are getting sodium metaborate, NaBO2, and also hydrogen gas. Reaction with Lewis bases. Diborane on treatment with Lewis bases. For example, we have here taken Lewis base NMe3 trimethyl, that is, it is ammonia derivative. Just replace on the hydrogen with methyl, you will get NMe3 or carbon monoxide, etc. And first it undergoes cleavage. So it is not another point, it is same line is continuing to form borane first. So first there will be formation of borane, which then react with Lewis base to form adducts. So these are two separate reactions, giving a mark here. First, it is reacting with 2NMe3, and see here it is dimeric form, but if you break it, you will get 2BH3. And as if two individual BH3 is now making adduct with NMe3. So you are getting 2BH3 dot NMe3 adduct. Okay. So that is it is written first undergo cleavage to form boron. So B2H6 first it will form 2BH3 and then it will react individually with this Lewis base. So this is Lewis base. This is also another example of Lewis base. In both cases it is 1:2 ratio we have taken. And we are getting 2 adduct molecules. How it reacts with halogens. Halogens react with diborane and it forms the corresponding halodiborane. Here the reactivity decreases in this order. That means chlorine will react first. There is a reaction which is with explosion, explosively even at room temperature. So it is clear how reactivity is when it is treated with B2H6. Then if it is bromine, reacts rapidly at 373 Kelvin. Rapidly, not explosively. Try to understand the difference. Explosively means very vigorous. Rapidly means it is fast, but not so vigorous. At 373, and iodine reacts very slowly, even if you are increasing the temperature. So slowly, even at still high temperature. So even you are increasing the temperature greater than 373 Kelvin, then also it is slow. So it proves how that is. All of them are reacting with B2H6, but the way they are reacting, it is obviously not same. Here, one H is replaced by one halogen atom, and the other halogen atom is making compound with this H, which we are getting from B2H6. So ultimately, we are getting B2H5X in general if you write it, and HX. Okay. The next reaction is basically mostly we'll see in organic chemistry. Very important reaction in organic chemistry. And we call this reaction hydroboration. So from the name what it means, hydro means obviously H and boration. That means there is some addition of units which is related to B and H. And here diborane reacts with multiple bonds such as CC double bond, or it may be triple bond. That is also multiple bond, right? And the solvent we use ether, and reaction is at room temperature. Here we have taken this alkene molecule which is not symmetric. See, we have 2 methyl group in the left hand side carbon and the right hand side carbon we have 2 hydrogen. In presence of BH3 and THF, THF is also ether type of solvent, tetrahydrofuran. Furan is this molecule, but if you remove these 2 bonds, you get tetrahydrofuran. Okay. And see, this is cyclic ether. So ether type of solvent we take. And here this BH3, if you write this molecule in this way, so one H is attached to the number 1 carbon and the BH2 unit is attached to number 2 carbon. Now, if you take any symmetrical alkene, suppose you have taken symmetrical alkene, that is ethylene, the simplest, then you will not be able to understand its regioselectivity. But if you take this type of unsymmetrical alkene, then you will be able to understand that the BH2 unit, it is always attached to that carbon which is less substituted, and H is attached to that carbon which is more substituted. So here number 1 carbon is more substituted and this one is less substituted. Okay. So this step is called hydroboration. But the reaction, it is not end of the reaction. There is further reaction going on. But if you consider the total reaction that is actually done in organic chemistry, then we have to consider the next step also. But if you simply focus on the use of, that is the chemical reactivity of BH3, then it is up to this point. Because further, whatever we are doing, there is no involvement of boron. So up to this point, this reaction involves net addition of H and BH2 groups across the multiple bonds, CC bond, double bond or triple bond. But the next step is now we are using hydrogen peroxide in alkaline medium, HO minus, alkaline medium. So here what is the change we are seeing? Only this BH2 unit is converted to HO unit. That is the only change happening. But this step is called oxidation step. This step is hydroboration and the second step is oxidation. Now, if you want to name this reaction, the full name will be hydroboration oxidation together. If you are simply saying hydroboration, then it is only the first step. If you are saying it is oxidation, then it is the second step. Okay, and together if you are saying net addition of H and OH, that is if you consider the first molecule, suppose I am considering the first molecule, and the ultimate result if you see, it is the net addition of H and OH across the double bond, and OH is added to that carbon which is less substituted, and that is anti-Markovnikov rule. So hydroboration along with the oxidation step, it has important application in synthetic organic chemistry, because here from CC double bond, from alkene, you are basically making alcohol, right? And then further this alcohol you can convert it to many other type of compounds. So that is why it has so many applications. And it is net addition of H and OH in anti-Markovnikov fashion. So Markovnikov is if the negative part of the reagent is added to most substituted carbon, but that is not happening here. It is the opposite thing that is happening. The negative part of the reagent, which is if you consider HOH, that is water, negative part is HO, and that is attached to less substituted carbon. So that is it is anti-Markovnikov, and the ultimate molecule is alcohol. Okay. Now here only the important steps you are seeing, but if you want to go into some details, then we have taken here another alkene molecule that is also unsymmetrical. We have taken CH3 CH double bond CH2. Only what is the difference? In the previous case we have two methyl group in the left hand side carbon, now we have only one. So see what is the difference we are seeing here. Though here BH3 is written, but actually we take B2H6. For simplicity, it is written as BH3, but actually it is B2H6. So in B2H6, first it will be clipped to the simple units, that is BH3. Now this BH3, the H part is added. Okay, let me change the H part is added to number 1 carbon, and the BH2 unit is added to number 2 carbon. Okay, this is the first thing that is happening. Now this molecule, if I write this part as R group, because it is alkyl group, so it will be RBH2. Now this RBH2, it is also equivalent to BH3. If I write it like this, just it is analog of BH3. RBH2, just imagine hydrogen in place of R. So it is just like BH3 unit. So this RBH2, it can also behave as if it is another BH3 unit. So that is why another alkene molecule, if you take this RBH2, now this BH2 part, that will be added to this terminal CH2, and the rest of the part that will be added to number 1 carbon. So see, if another R group is attached, that is CH3, CH2, CH2, it is attached, then it will be structure like this. So this is as if equivalent to R2BH. Now this R2BH, it can be again added to another molecule of alkene. So in this way, total 3 alkene molecules. This is the first alkene, this is the second alkene, and this is the third alkene. Total 3 alkenes are added to this BH3, and ultimately the compound that you are getting, it is as if equivalent to R3B. So these are the details of step. If you are interested, you can understand this. There is formation of 3 alkyl groups are now attached to B. Okay. And if it is so, after that we have to treat it with H2O2 alkaline condition. So this is our R3B. So R3B is the general way of writing, because here it is propene molecule, 3 carbon CC double bond propene. propene. But it may be any other alkene. So that is why in general you can write it as R3B. This R3B, when treated with H2O to HO minus, ultimately we are getting this alcohol, and the boron part is removed in the form of boric acid, that is H3BO3 or BOH3. But ultimate reaction that is shown in the first diagram. Okay. Where from alkene we can make alcohol in anti-Markovnikov fashion. We have a question here which is related to inorganic benzene, that is borax. It is asking that what is the hybridization state of boron and nitrogen in inorganic benzene respectively. So inorganic benzene is B3N3H6, and we have seen the structure. And there is hydrogen bonds. That is hydrogen, not hydrogen bond. I mean to say hydrogen atoms are bonded. Now hybridization, before going to hybridization, first I will write the electronic configuration of boron in ground state, the valence shell obviously. It is 2s2, 2p1. 2s, this is 2p, it is 2s2, 2p1. But when it is in excited state, now this electron, I will write it here. Okay. Similar thing if you do for nitrogen, it is actually 2s2, 2p3. But one electron I will shift in p, and as a result now it will be like this. This is also 2s, this is 2p. Now there will be sp2 hybridization. sp2 hybridization means 1 sp, 2p. So there will be 2 sp2. So these two are sp2, sp2 and one pure p orbital, which is not part of hybridization, right? Sorry, total 3 sp2 will be there because 1s and 3p. Total number of orbitals it is same after hybridization, and this is pure p. Similar thing if we do here, that is sp2 hybridization. Now there will be total 3 new sp2 and one p orbital which is not part of hybridization, that is here. If you place the electrons now, so here we have this lone pair. This is basically lone pair. Now this 3 sp2, it will form 3 covalent bonds with this 3 sp2 of nitrogen. As you can see, surrounding nitrogen, sorry, what I am trying to say, nitrogen will use its 3 sp2 so for bond formation with 2 boron and 1 hydrogen. Similarly, boron will use its 3 sp2 for bond formation with 2 nitrogen and 1 H. But now the next thing that will happen, this lone pair can be donated to the vacant orbital of B, and that is why now there will be some bond formation like this. So that is why now boron will gain some negative charge and nitrogen will be having some positive charge because it has completely donated electron and boron has accepted electron. But important point that we have seen here, the hybridization is sp2. So when we are solving this problem, you will be able, that is idea about its structure, it will be clear to you. That is how all these bonds are formed. Okay. So nitrogen is using sp2, 3 sp2 orbital for 3 covalent bond formation. But the fourth one is like coordination bond where both the electrons are coming from one atom going to another. Okay. So here both are sp2. We have options. It is saying that boron is sp2, nitrogen is sp3, like this. And another thing also, see, the molecule is planar, right? So sp3 hybridization is not possible at all because if it is sp3, it has to then lose the planarity structure. So that is not another common sense we can apply, that sp3 hybridization is not possible. So here both are basically sp2 hybridized. Okay, we have one problem here also. This is also related to B2H6. 3 moles of B2H6 completely reacted with methanol. So here we have to remember that equation. Remember in the chemical properties section, we have seen B2H6 reacting with different types of compounds, alkali, acid, halogen, Lewis base. But when it is reacting with methanol, then it is, the question is asking, then the number of moles of boron containing product. So once the reaction is done, in the right hand side, the boron related molecule that will be formed, we have to find the number of moles of that boron compound. So to answer this question, you just have to know the balanced equation. The balanced equation of B2H6 plus methanol, because it is saying 3 moles. So from 3 moles of B2H6, how many moles of the boron containing product will be formed, that we have to know. So not just what product is formed, that is important to know, but also we have to balance it. So this is the balanced equation. From 1 mole of B2H6, we are getting 2 moles of BOCH3, which is trimethyl borate. Fine. That means for 1, we are getting 2 moles of boron containing product, which is BOCH3. So when it is 3, obviously double amount will be 6. So when it is 3 B2H6, the boron containing compound formed will be 6 BOCH3. So here the answer should be 6. Okay, the number of moles of boron containing product. And remember, the question can be framed in another way, that 3 moles of B2H6 reacts with how many moles of methanol. So when it is 3, then it will be 6 into 3, that is 18. Fine. It is integer type of problem. And finally, we'll finish this compound with its application, which is that is Diborane. In some applications we have already seen. Remember, first of all, it can be used as reducing agent because it is the source of H minus. So that is one application. And also we have seen how these compounds are formed. So preparing a number of boron hydrides, that is also another application. There is rocket propellant, borosilicate type of glass. When we manufacture, then it has application. It can be used as a catalyst in rubber vulcanizer in polymerization reaction. So though it remains in dimeric form, but it is still there is some electron deficiency, and that is why it can be used as Lewis acid catalyst also. Doping agent in manufacturing semiconductor devices, and welding torch. That is welding means when we connect two metal parts by melting it. So high temperature is required. So making that type of torch also, it has application. So B2H6, this compound we have finished. Okay. Next compound is now aluminium compound. So under boron, total 3 boron molecules, B2H6, H3BO3 and borax. These 3 molecules we have completed. And under aluminium, there is aluminium chloride, and once it is finished, the next aluminium compound is alum. First, we'll start with preparation, industrial scale. So when it is large scale, it is prepared by chlorinating aluminium metal directly, or that is you are treating aluminium with chlorine gas, the first equation, or you can treat aluminium with HCl, and the temperature is high, 923-1023 Kelvin, and these reactions are exothermic in nature. So you can treat it with chlorine or you can treat it with HCl. Both are sources of chlorine atoms. In the first case, we are directly getting AlCl3. Here we are also getting hydrogen gas. We can also make it starting from this aluminium compound, which is aluminium hydroxide. Aluminium hydroxide, it is basic in nature. It is treated with HCl, and aluminium trichloride AlCl3 is formed. Finally, this reaction mixture is evaporated to obtain hydrated AlCl3. Evaporated means to remove this water. The third method, where the starting material, that is the aluminium sources we are using, is alumina, that is nothing but aluminium aluminium oxide, and we are treating it with carbon and chlorine. So heating a mixture of alumina, that is Al2O3, with coke, which is nothing but carbon, in a current of chlorine, we are getting AlCl3, and oxygen is removed in the form of carbon dioxide. The fourth method is starting from copper chloride. Which copper chloride? Copper in 2+ oxidation state. It is cupric chloride. Another chloride of copper is possible, which is cuprous chloride, where copper is having oxidation state +1. And when it is +2, we call it cupric. When aluminium metal is treated with this copper 2 chloride, aluminium is more reactive. If you consider its metallic property with respect to copper, aluminium is more reactive, and that is why it is before reaction it is 0 oxidation state metallic form, and copper it is in 2+ oxidation state, but now it can displace 2+. That means now copper will gain electron from aluminium. Because aluminium is more reactive, so its reducing capacity is high. It will feed electron to Cu2+, and itself will be converted to AlCl3, that is now it is in +3 oxidation state, and see, copper is now reduced. So it is a kind of redox reaction. Now AlCl3, previously we have chloride salt of copper, now we have the aluminium salt. Okay, so these are the 4 methods for preparation. Now the structure part will not be able to finish, so I will not start it. So we are ending the session in here. That is the preparation methods. Total 4 methods we have seen for aluminium chloride. Next day we'll see its properties and structure. We are ending the session here. Thank you for listening.